This is our third lecture video for Chapter 13, Kinetics. And we're beginning by looking at the rate law. The rate law of a reaction is the mathematical relationship between the rate of the reaction and the concentration of the reactants, and also homogeneous catalysis as well. The rate of a reaction is directly proportional to the concentration of each reactant raised to a certain power. For the reaction where A plus B goes to products, the rate law would have the form given below, where rate equals a constant K, which is lowercase, so this is our rate constant, times the concentration of one of our reactants A raised to some power N, and the other reactant raised to some power M, where N and M are called the orders for each reactant. So these exponents here represent the order of the reaction. Here are some example rate laws. For acetonitrile, during the isomerization reaction, the rate law expression is rate equals the rate constant times the concentration of the acetonitrile. Here in the second reaction, notice that in the rate law expression, the order with which this reactant is 3/2. And in this third reaction where we have two N2O5s, they decompose to make NO2 and O2. The rate law expression is the rate constant times the concentration of N2O5 raised to the first power. So what I'm showing you here is that you can't just look at these reactions and know the orders of the reaction. These orders have to be experimentally determined. So you just can't say, oh, there's a 1 in front of this acetonitrile, it must automatically have a 1 here. No, that's actually going to depend upon the mechanism, so that has to be experimentally determined. So for the second reaction, it was determined that the experimental rate law is K times the concentration of that reactant raised to the 3/2 power. Now, it's not too often that we'll see very many reactions dealing with fractions. Most of the reactions that we're going to be looking at are going to be whole numbers for the orders of the reactions. And you can have negative orders of a reaction, and a negative order of a reaction indicates that it's a negative catalyst. So in this case, the mercury 2+ is a negative catalyst, and increasing its concentration actually slows the reaction down. Now the rate law, we said, can only be determined experimentally, either one of two ways. We can either look at the initial rates or determine it graphically. So we're going to start by looking at initial rates. So in the initial rates method, we're comparing the effect on the rate by changing the initial concentration of reactants one at a time. And this is what we're actually going to be doing in lab. So for this reaction here, we're looking at 6 I- reacting with BrO3- and 6 protons to make 3 equivalents of iodine, aqueous, bromide, and 3 equivalents of water. If we write the rate law expression of this, the rate equals the rate constant times the concentration of I- raised to some power, the BrO3- raised to some power, and the proton concentration raised to some power. So the orders with respect to each of these reactants has to be determined experimentally. Here in this table, I've got some data that's been collected. And we've got 4 different trials where we're changing the initial concentration of the different reactants and finding the rate of the reaction. Now, to determine the order of the reaction, we have to find 2 systems where only one thing is changing. So I'm going to look at trial 1 and 2. If I look at trial 1 and 2, the concentration of the BrO3- stays the same, and the concentration of the H+ stays the same. What does change is that the concentration of the I- has almost doubled. And when the concentration of the I- doubled, we saw the reaction rate almost double itself. So we want to find that order with respect to that reactant. So since I'm using trial 1 and 2 to compare, I'm setting up a ratio of looking at trial 1 to trial 2. And I'm just writing the rate law expression for trial 1. So the rate equals K times I- raised to the M, BrO3- raised to the N, H+ raised to the P. And I'm doing the same thing for trial 2. Now I can plug in the values that I know. So we said the rate of trial 1 was 29, the rate of trial 2 was 50. So this is where this ratio came from. Now, also got the K on both top and bottom. Those K's will cancel each other out, so I don't have to know the rate constant there. And because the concentration of the BrO3 minus did not change, that's the same thing as multiplying this whole thing by 1. So these will cancel out. And because the concentration of the protons stay the same, this portion of the equation will cancel out as well. So this reduces down to 29 over 50 equals 0.002 over 0.0039 raised to some power m. And m is the order with respect to I minus. So to solve for m, I'm going to take the log or the natural log of both sides. So if I take the natural log of the 29 over 50 and I take the natural log of the 0.002 over 0.0039, I get that this whole thing is the same thing as m times the ln of 0.5128. Because when I have this ln, I can bring this exponent out into the front with my rules of logs. So m equals the ln of 29 over 50 divided by the ln of 0.5128. And if I put this into my calculator, I get a value of 0.81. Now because orders of reactions are typically whole numbers, we're rounding this to the nearest whole number, which is 1. And this will give you an idea of what kind of representative data you will get in lab, because this is something that you're actually going to be doing in lab with this system. So we found the order with respect to m. We can repeat this process and find the orders with respect to BrO3 minus and with the H plus. So we can find N and P. We just have to make sure that, for instance, if we're looking for the order with respect to the BrO3 minus, we're looking for a change in the concentration there, but the others have to stay the same. So in that case, I can look at trial 1 and trial 3 because the concentration I minus stays the same, the H plus stays the same, but the concentration BrO3 minus goes from 0.0078 to 0.0157. So if you want, you can pause the video and practice and see if you can figure out what the orders are with respect to N and P to make sure you understand this concept. Okay, so we said that we can determine the rate law two different ways, one by the initial rates and the other graphically. So we just looked at how to do the initial rates. Now we can see how graphing can help us determine the rate. The second way that we can determine the rate law is by using graphical methods. And remember that when we looked at concentration of a reactant versus time, we could get the slope at any point in time, and the slope of that line, of that tangent line, gave us the rate of the reaction. Now if we do several different types of plot, we can figure out the order of a reaction based upon whether or not we get a straight line. So let's look at our first example. In the first example, we're going to be looking at a plot of concentration versus time. So if the graph of concentration versus time is a straight line, then the exponent on A in the rate law is 0. So it's 0th order with respect to A. And the rate constant is going to be equal to the negative slope value. So let's say we do that plot and we don't get a straight line. Now we can try another type of plot where we plot the ln of A versus time. So if graph of the ln of concentration of A versus time gives you a straight line, then the exponent on A in the rate law is 1, so it's a first order reaction. And if that's the case, if you get that straight line there, the rate constant is equal to the negative of the slope. But let's say you try that reaction or you try that graph and you still don't get a straight line. The next thing that you can try is plotting the inverse concentration versus time. So if the graph of the inverse concentration versus time is a straight line, the exponent on A in the rate law is 2. So this means it's second order with respect to A. And in this case, the rate constant will equal the slope. So the next couple of slides will actually break these three different graphs down a little bit more. Now going back to looking at the reactant concentration versus time. For a 0th order reaction, notice that we have a straight line. So we're starting off with a concentration of 1 for our A. And as time progresses, we start to lose A, and it goes in a straight line. So no matter what the concentration of A is, you're still losing at the same rate. because you got this straight line here. So this would be zeroth order with respect to A. But notice if the reaction is first order with respect to A, then we get a bit of a curve to this line. And if it's second order, the graph is even more curved. So as the concentration goes down over time, it gets a bit of more of a curved shape to it. So remember, let's say the rate is zeroth order. So anything raised to the power of 0 goes to 1. So the rate equals k. Well, in this first order, we have an understood 1 here. So the rate is going to be proportional to the concentration of A. So if you double the concentration of A, the rate of the reaction should double. And if we're talking about a second order reaction, if I double the concentration of A, so let's say I go from 1 to 2, that's the concentration squared is how I get the rate. So if I double A, the rate of the reaction should quadruple. Now let's look at the rate versus the reactant concentration. So the rate of the reaction is on our y-axis and our concentration is on the x-axis. So a zero order reaction, because it's raised to the 0 power, the rate is going to be the same, because remember this is the same thing as rate equals k. So the constant, so the rate is a constant, so you got a flat line, so the rate isn't changing as the concentration of A changes. But for a first order reaction, if we increase the concentration, we increase the rate of the reaction by the same amount. And for a second order reaction, let's say we double our concentration of A, we're going to quadruple the rate. So this is why the rate of the reaction versus the concentration has this curved portion to it, because it's raised to the second power. Now the rate law expression, remember that relates the rates to the concentration. So if we had a rate expression of rate equals k times the concentration of A times concentration of B raised to the second power, this relates the concentrations to the rate. Now remember, the rate of the reaction we got by taking the slope of the tangent line of the concentration versus time, but remember that gave us rate, so that we're actually taking the derivative of those lines to get the rate expression. Well, in calculus, the reverse of doing a derivative is to do an integration. So just like subtracting is the opposite of addition and division is the opposite of multiplication, integration is the opposite of taking the derivative. So what we're doing is we're creating what we call the integrated rate law. So you take the rate law expression and you integrate it. And this is going to allow us to look at concentration and how that relates to time. So the integrated rate law for the first order is expressed as the ln of the concentration of A equals negative kT plus the ln of the initial concentration. So this sub-zero here just means the initial concentration of A. So we can find the concentration of A at any point in the reaction if we know the initial concentration here and the K value. Now half-life expressions fall under this category, and the half-life of a reaction is the length of time it takes for the concentration of the reactants to fall to half of its initial value. And the half-life of a reaction depends on the order of the reaction. This is just a blow-up of the previous slide where we're looking at the half-life. So here we're looking at initial concentration of 1 molar, and that time 0. And after a certain point of time, half of the reactants remain. So this first half-life was 100 seconds. And then after another half-life goes past, then you halve the concentration again. And after another half-life, the concentration has gone down to another half. So notice how, here we have 6, and this went down to 3, so 3, 6, 12, and then 24. Okay, so we're going to focus on the different types of orders of reactants, and we're going to focus on the zeroth order first. The rate law expression for a zeroth order reaction is the same as the rate equals the rate constant, because remember that concentration of A is raised to the 0 power and that disappears, so it's the same thing as rate equals K. So for zeroth order reactions, the rate of the reaction remains constant. The integrated rate law expression for a zeroth order reaction is A equals negative KT plus the initial concentration of A. And if you look at this, hopefully see something that looks like a line. So the concentration of A would be our Y and the T would be our X. So if you plot the concentration of A versus time, you get a straight line. And the slope is going to be the same thing as negative K. And the y-intercept will be the initial concentration of A. So this graphical method is how you can get the rate constant K, by plotting the concentration versus time. The half-life expression for a zeroth order reaction, so T equals 1/2, this is the half-life, equals the initial concentration divided by 2K. So remember, K is the rate constant. And the units for the rate constant for a zeroth order reaction are going to be molar per second. Now, a lot of students spend a lot of time trying to memorize the units for the different orders of reactions, and it's really easy to actually solve for this value. So if the rate of the reaction is expressed as molarity per second, because remember we're looking at change in concentration over time, so if that's the rate of the reaction, so A is the concentration, because the brackets mean concentration, that's in molarity, but it's raised to the 0th power, so that disappears. So if our units for our rate have molarity per second, the units on K have to be molarity per second too. Now let's look at the first order reactions. And remember, first order reaction, this is where A is raised to the 1st power, so the rate law expression equals rate equals K times the concentration of A raised to the 1st power. And the integrated rate law expression is the ln of A equals negative KT plus the ln of the initial concentration. So in this case, we're plotting the ln of A versus time. So the ln of A is on the y-axis and time is on the x-axis. So from a graph, you can get the rate constant K, because the slope is a negative K. And the y-intercept is going to be equal to the ln of the initial concentration. So if you do a plot of your ln of your concentration versus time and it gives you a straight line, that tells you it's first order with respect to that reactant. And the half-life expression, so the half-life for a first order reaction equals to 0.693 divided by the rate constant. So notice that the half-life for first order reactions are constant, whereas if it's 0th order or 2nd order, you'll see that the half-life actually changes. But for a first order reaction, the half-life is always consistent. So in this graph here where we're looking at half-lives, notice that the half-life is always 100 seconds. So this would be an example of a first order half-life. And the units for the rate constant on a first order reaction are the same thing as the inverse second. So let's see how we can solve for that. So if the rate is molarity per second, and I'm looking for the units on K, and I know that I have my concentration of A, and that's in molarity. So the units on K, if I solve for this, I divide both sides by m, K has to be 1 over seconds. So this is where I get my units for K. So here's the last type of order we're going to be looking at, the second order reactions. So remember, the rate law expression for a second order reaction is rate equals the rate constant times the concentration of what you're looking at raised to the 2nd power. So this is that second order. And the integrated rate law expression for a second order reaction is the inverse concentration equals to K times time plus the inverse of the initial concentration. And it's this graph here that produces a straight line for a second order reaction. So if we plot the inverse concentration on the y-axis and time on the x-axis, the slope of the line will give me my rate constant, and the y-intercept, I can find my initial concentration. And the half-life expression for a second order reaction, T1/2 equals 1 over K times the initial concentration. So remember, for zeroth order reactions and second order reactions, the half-life is going to depend upon the initial concentration, but for a first order reaction, it's constant, so it stays the same, so it doesn't depend upon the initial concentration. And the units for the rate constant for a second order reaction are inverse molar and inverse seconds, because if rate has units of molarity per second, and I'm trying to find the units on K, and the concentration of A is squared, and that's molarity squared. So I need to solve this for K, so I divide both sides by m squared, divide by m squared. So this will cancel out. This will disappear, that 2 disappears. So the units on K are the same as 1 over molarity times second. So I've told you that we can figure out the order of a reaction if we graph it. So here's where we're looking at applying that method. So the first 2 columns here, we're looking at time and the partial pressure of NO2. And the reaction that we're interested in is 2 equivalents of NO2 going to 2 equivalents of NO and 1 equivalent of oxygen. So notice how we go from 2 moles of gas to 3 moles of gas. And in this graph, we plotted pressure versus time. So this would be similar to plotting concentration versus time. So in this case, notice how we don't get a straight line. So we're looking at the data for the red line. So this isn't a straight line. So since we plotted the concentration versus time and we didn't get a straight line, we know it's not zeroth order. If we plot the ln of the pressure versus time, we're testing for a first order reaction. So notice that we still don't get a straight line. So this tells us that it's not first order with respect to the NO2. Now in this last graph, we plotted the inverse pressure of the NO2 versus time. So in this case, we get a straight line. So what that tells us, because we get a straight line when we plotted the inverse pressure versus time, this is a second order reaction. So second order, yes. First order, no, because we don't have a straight line. Zeroth order, no, because we don't have a straight line. Now in this table here, we're just summing up some of the information that we had on several different slides. We're putting it all in one place to help you summarize what's going on. So in the first line here, we've got the information for a zero order reaction. So we have the rate law expression for that, and the units on K, the integrated rate law, and what kind of plot that you need to do to see if you get a straight line. So it's the concentration of A versus time, and it's the negative slope, negative of the slope, that gives you your K value. And here we have the half-life expression for a zeroth order. And so again, the rate for the first order, and here you have the information for the rate of a second order. So all this is we've discussed on other previous slides. It's just all put into one. So this ends our third lecture for kinetics.